I'm very sorry that we are not directly working on the multi-neutron clusters. But all nuclear structures are affected, of course, by the nuclear correlation. So I hope our spec studies is much in the line of this theme of this workshop. Okay, this is my the content of my talk. First, I'd like to start with nucleosynthesis in the universe. This figure shows the nuclear chart and shows the nucleosynthesis processes after the Big Bang nucleosynthesis. There are many nucleosynthesis processes in the universe. However, the major processes, stellar fusion, slow neutron capture process, and rapid neutron capture process. And the rapid neutron capture process, our process goes through very neutron-rich regions. And the red dotted lines indicate the most neutron-rich isotope of each element synthesized in the laboratories so far. So there is a vast region which is unexplored so far. It's called blank spot between the known nuclei and our process path. So we are promoting the KISS project to produce the neutron-rich nuclei around the N equal 126 and the actinides. And further, we are proceeding the update of the KISS, so-called KISS 1.5, to go to further neutron-rich size. First, I'd like to focus on the spectroscopy of neutron-rich nuclei around N equal 126. These figures show again our process path indicated by red boxes, and these figures show a part of the nuclear chart around N equal 126. The measured half-lives are classified by different colors, and the blue boxes indicate the stable nuclei. So as you see, even near the stable nuclei, many nuclei are still unknown for their lifetime and masses. So we will produce those nuclei and perform the decay spectroscopy in terms of the half-life and decay scheme, and laser spectroscopy for the charge radius, magnetic dipole moment, electric quadrupole moment, and as well as the mass spectrometry. So how such experiment, how such the nuclear properties has an impact on our process investigation. These figures show the deviation of our abundance pattern by changing the half-lives by one order of magnitude for different mass models. Each mass model shows a large deviation of the abundance patterns by changing the half-lives. So the half-life is one of the most important parameters to investigate our process nucleosynthesis. This figure shows the sensitivity of our abundance pattern to lifetime uncertainty for different astrophysical models for our process. The significance, each model shows the significance of the N equal 126 nuclei for the abundance patterns. So what does the theoretical models say for the lifetime? This figure shows the theoretical predictions of the half-lives of N equal 126 isotones. This region is our process waiting point regions. So the various theoretical models give the deviation of actually the one order of magnitude of the lifetime. So the experimental data is important to give the input to the theoretical models to improve the prediction of the process nuclei. So why the theoretical prediction is difficult in this region? It is because this is located as a competition region between the first forbidden and allowed transitions. As shown in this figure, where the blue color indicates the region, where the first dominant, first forbidden transitions are dominant. For example, in the case of tungsten, this figure shows single particle levels for the proton and neutrons respectively. And the tungsten fills 811 half states almost with 2 proton vacancies. And the most beta decay goes from the odd parity of the neutron states to the even parity proton states, so with a fast forbidden transitions. And such single particle levels are affected by the deformation. Actually, this nuclear region is located in the nuclear deformed regions, and the neutron numbers is approaching to the neutron magic number 126. The shape is changes from the prolate to the oblate, and finally goes to the spherical. And in the region of the neutron deficient side, this figure shows the charge square radius for various elements, and in the case of mercury, it shows the staggering of the charge square radius with odd and between the odd and even neutron numbers. So the, not only the measurement of the lifetime and mass is directly, but also the investigation of the nuclear structure is important to reveal the properties of the nuclei in this region. So we perform the, such a nuclear spectroscopy in these regions. However, it is a blank spot. It is difficult to produce. So the issue is how to produce those nuclei. One of the methods to produce the exotic nuclei is fragmentation and the infrared fission. They are adopted in the RIBF, Friebe and Fair. However, such a reaction goes to the has a feature of the subtractive features, so goes to the lower left direction from the target nucleus. We'd like to go to the lower right side to produce the neutron-rich nuclei from around N equal 126 regions. So this reaction is not much with our purposes. And another reaction is the fusion reaction around the Coulomb barrier, and this is adopted as a Garis at Riken and spiral 2 S cubes at Garnier. However, such a reaction has additive features, goes to the upper right direction, so it is not much our purpose. So we adopted multi-neutron transfer reactions which occurs around the Coulomb barrier and above the Coulomb barrier. They show they give the exchange of the proton and neutron between the colliding projectile and target. And it has additive and subtractive features and goes to the all direction. So by adding neutrons and subtracting protons, we can access to the lower right directions. So we are using the multi-neutron transfer reactions from the stable platinum 190 target to go access in these neutron-rich regions. So the multi-neutron transfer reaction is a characteristic reaction in the low-energy heavy ion reaction. This figure shows the classification of the low-energy heavy ion reactions as function in terms of the impact parameters. And this figure shows the differential cross sections as function of the orbital angular momentum, and the impact parameter. As the impact parameter becomes smaller, the reaction regime changes from the elastic scattering, Coulomb excitation, direct reaction, quasi-elastic, deep inelastic collision, quasi-fission, and finally go to the compound nuclear formation. So the multi-neutron transfer reactions is located in the reaction regimes ranging quasi-elastic, deep inelastic collision, and quasi-fissions. Such a reaction is characteristic for the heavy ion reactions. They are not seen in the light ion reactions. So such a reaction is not well understood, and the cross-section is unknown. So we have performed the experiments to check the feasibility of the multi-neutron transfer reactions to produce the neutron-rich nuclei using the xenon beam impinging on the platinum target. We have used the Vamos spectrometer as a Garnier. And we have measured detected the projectile-like fragments, and the target-like fragment distributions were deduced. These figures show the experimental results for the production of iridium, osmium, rhenium, and tungsten with 1 to 3, 4 proton pickup channels. The abscissa indicates the mass numbers, and the dots indicate the experimental data. The blue histograms indicate the grading calculations results, and the neutron deficient side, there is a large discrepancy between the measurements and the grading calculations. It is because of strongly damped collisions with N over Z equilibration, which is not included in the grading calculations. However, at the neutron-rich side, around n equal 126, they are contributed by the weakly damped component with less particle evaporation, and the grading calculation includes such evaporations and match to the such weakly damped regimes. So it gives a relatively good agreement between the measurement and the calculations. So the n equal 126 nuclei seems to be produced relatively much. So encouraged by these results, we have started the KISS project. However, there is other experimental problems to use the multi-neutron transfer reactions for the spectroscopic work. This figure shows the ease of the various nuclei produced in the multi-neutron transfer reactions. So the many nuclei are produced simultaneously. So if we'd like to measure one species of the nuclei, the other nucleus has becomes the background. So, and this figure shows the excitation functions of the producing the n equal 126 isotones. But they are the primary fragments just produced in the reaction, and they are excited. When the laboratory energy is higher, the excitation energy becomes higher and higher. And after the evaporation, this gives the excitation functions to produce the n equal 126 isotones, and we need to optimize the reaction energies and the target thickness. And if we'd like to perform the spectroscopy of osmium 202 produced from the platinum 198, this figure shows the correlation of the energies and the angles of the produced osmium 202. It has a large and low energy distribution and also the wide angular distribution around the grazing angles. So we need the development of the experimental techniques to effectively collect, separate, and identify reaction products for the nuclear spectroscopy. So we have constructed KISS. It is a KK isotope separation system as a weekend RIBF facility. We settled the KISS at the E2 laboratory in the old facility, and using the RELAC2 linear accelerator and RRC weekend link cyclotron, the heavy ion beams are accelerated up to the 10.75 MeV per nucleon. So this figure shows the schematic view of the KISS facility. The beam from the weekend ring cyclotron goes to the gas chamber, and the reaction products are collected by the gas cell. I will explain details in the following slides. And the reaction products are ionized by the lasers and mass separated by the dipole magnet and transported to the decay spectrometer and the mass spectrometer. Okay, this figure shows the schematic view of the gas cell chamber. The beam from the weekend ring cyclotron, the xenon beam goes to the energy degrader to tune the optimum energies and hit the targets. And the reaction products has certain angles, and they pass through the polyimide films into the gas cell. Gas cell, this figure shows the gas cell. We call this toner-shaped argon gas cell because the beam goes through the beam pipe to the beam dump. to avoid the cause a dense plasma in the argon gas by the beam injections. So the reaction products are summarized and neutralized in the argon gas. This figure shows a cross-sectional view of the summarized iridium ions in the argon gas cell. By collision with the argon gas atoms, those reaction products are neutralized. And such neutral atoms are transported by the laminar gas flow, and before the exit, they are irradiated by the lasers for the element selective ionization. And such ions are transported by the RF ion guides and accelerated by a high voltage and mass separated by the dipole magnetic field. So using the gas cell, we can efficiently collect the reaction products, and by neutralization and laser resonance ionization, we can select the one element. And using the dipole magnet field, we can select the mass. So we can choose one species of the nuclei from the various reaction products for the removing the background for the spectroscopy. Such nuclei, such ions are transported to the decay spectrometer. This figure shows the beta counters, and the beam is stopped at the tape, and the beta rays from the such short-lived nuclei are detected by the multi-sampling, multi-segmented proportional gas counter. And it was surrounded by the 4 high-purity germanium chloride detectors for the beta and gamma spectroscopy. Such a decay spectrometer is located here, and the KISS beams can be switched to the decay spectrometer and also to the mass spectrometer. This figure shows the mass spectrometer setups. The KISS beam is stopped in the helium gas cell. This is a helium gas cell, so the ions are not neutralized. They are stopped as ions and transported by the DC electric field and RF carpet, and transported by RF ion guides, and injected MR-TOF mass spectrograph. MR-TOF is a multi-reflection time of flight mass spectrograph. This slide is made as originally as animation, but this is PDF file, so the animation doesn't work. So the ions are injected in MR-TOF, and there is 2 reflection electrodes, and the ions can be reflected these electrodes many times. For example, that is 1,000 times. So the MR-TOF has a dimension of about 50 centimeters. However, the reflection of the 1,000 times actually the ions flight in the distance of 1 kilometer. So using such measuring the time of flight in such a long distance, we can precisely measure the ion masses. So the mass resonance power is larger than 400,000. This figure shows the case of the TF spectrum of the A equal 190 isobars, and we can clearly separate the isobars, osmium 190 and iridium 190 and radium 190. Okay, this figure shows the experimental results performed as a KISS. The blue and red circles indicate the isotopes we have extracted for the decay and laser spectroscopy respectively, and stars indicate the ions which we have performed the mass spectrometry. I will show some results highlighted in this figure. First one is the beta gamma spectroscopy of osmium 195 and osmium 198. This figure shows the growth and decay curves of the beta ray detection, and we have measured the half-life. It is already measured, and it is consistent with the literature value. However, we have determined the decay schemes for the first time and reduced the log FT values. They are consistent with the first forbidden transitions and the supports the 3½ minus state for the osmium-195 ground state. And this figure shows the case of the osmium-198. We have also measured the growth and decay curves, and we measured the half-life for the first time, and determine the decay schemas. Again, all transitions are the first forbidden transitions, and supports 0 or 1 minus spin parity for the helium-198 daughter nucleus. Okay, so this figure shows the single particle levels for the osmium. In the case of osmium, this H11 half state is filled. So the all beta decay is expected for the first forbidden transitions, and actually our experiments show that all beta transition is first forbidden transitions. So the dominant transition is first forbidden transition, so the theoretical prediction for the half-life is difficult. This figure shows the experimental data of the half-life of osmium isotopes as a function of mass number. Red indicates the results of the KISS measurements, and the black circles indicate as experimental results. The different 3 lines indicate the prediction of the different theoretical models. So any theoretical model cannot reproduce all experimental data by one theoretical model. So I'd like to ask theoreticians to improve the theoretical models which consistently reproduce all half-lives by one model. Okay, this is a gamma ray spectroscopy of tantalum 187 isomeric states. The multi-neutron transfer reactions can produce also the isomeric state. And this figure shows the gamma-gamma coincidence energy spectrum and coincidence data. We could construct the decay schemes from the high K isomeric states and reduce the half-lives. This figure shows the moment of inertia in inverse of the moment of inertia in 9 half-state bands, rotational bands, function of the spins. So the red lines indicate that this is tantalum 187, and the blue lines indicate the isobars, rhenium isobars 189. Z decreases from the rhenium to the tungsten, tantalum. The beta to deformation increases and actually plays reduced roles. This shows such a staggering. In the case of rhenium, it shows such a staggering. However, in the case of tantalum, the staggering appears only the high excited states. Okay, this figure shows the result of the mass spectrometry of the tungsten 189, and the 192. This figure shows the MR time spectrum for the different mass numbers, and by turning on the laser and turning off the laser, we clearly identify the tungsten 189 and rhenium 192. And this shows the results of the atomic mass deviation from the AME 2020. And using this mass data, we could reduce the 2 neutron separation energies for the tungsten and rhenium as a function of the neutron numbers. So we could confirm the shape transition from the prolate to oblate. The red lines indicate the 2 neutron separation energies assuming prolate deformation, and blue indicates the 2 neutron separation energies assuming the oblate by the theory. And we can see the transition from the prolate to the oblate for the around the rhenium 192. Okay, this is the result of the laser spectroscopy of osmium 194 and 196 using the MR-TOF mass spectrograph. Because osmium 194 has this is unstable nucleus. However, the half-life is very long, 6 years. So it is too long to identify osmium-194 by the decay measurements. So MR-TOF can clearly identify the osmium-194, which are separated from the background nucleus of platinum-194. So counting the osmium-194 and changing the laser wavelengths, we could get the hyperfine structure of the osmium-196 and 194, and we could deduce the variation of the mean square radius for the osmium isotopic chains. And assuming nuclear models, we could deduce the absolute deformation parameters for them. For the case of osmium-194, the experimental values is consistent with the theoretical models indicating the oblate deformation. However, in the case of 196 osmium, the theoretical values are different from the experimental values is different from the theoretical values, indicating triaxial asymmetry. Okay, so I'd like to move to the spectroscopy of neutron-rich actinide nuclei. We are also investigating the neutron-rich actinide region. This is important for the R process nucleosynthesis because the existing uranium and thorium are only produced by the R process. The beta decay from the R process path populates the nuclei in this region, and the white box nuclei decay, cause alpha decay and reach the uranium 238 or the thorium 232. Above the mass number above 252, they cause the fissions. So the nucleus between the A equal 232 to the 252 contribute to the population, the present population of the uranium 238 and 232. So these nuclear properties in this region is important, so we try to produce those neutron-rich nuclei by multi-neutron transfer reactions. However, this is also another region of the nuclear deformation. So the deformation is important nuclear aspect, and such a nuclear deformation drastically changes the single particle levels for the protons and neutrons, as shown in this figure, and it causes a deformed magic number as the neutron number 152 and 162. And between these deformed magic numbers, the single particle levels changes as function of the atomic number. In this case, shows the calculation of the difference of single particle energies compared to the 11 half states. And the 7 half states is sensitive for the beta 4 parameters. So it is drastically changes the ordering by changing the deformation, which is affected by the pairing effect of the nucleons in the nucleus. And this figure shows the evolution of the nuclear shapes as a function of neutron numbers, and beta 2 parameters are changing like this. And it is predicted that the depression of the central densities as beta 2 parameters increases like this. Okay, so we have performed the mass spectroscopy of the neutron-rich actinides using the uranium beam impinging on the platinum target. This figure shows the nuclei which we extracted from the multi-neutron transfer reactions and measured the masses by the MR-TOF mass spectrograph. This figure shows the all data of the mass, and we discovered the uranium 241 for the first time, and measured the mass of the uranium 241 and uranium 242 for the first time, like this. Okay, so we'd like to go to the more neutron-rich side. So we are now promoting the update of the KISS. It is called KISS 1.5. The strategies don't separate but measure multiple species at once to increase the efficiency of the measurements. This figure shows a schematic view of the KISS 1.5. This is a KISS system which exists already. And we will construct the KISS 1.5 as shown in this line. We are using the helium gas cell, which collects the reaction product as ions, and all reaction products are transported to the mass spectrograph just after the gas cell and simultaneously measure the various reaction products. And also, such reaction products can be transported to the existing spectroscopic lines, selecting the masses. This system, barrier mass range separator, can select one mass or transport the 5 adjacent masses simultaneously, and using the mass Emaltov system, we can identify the neutron number as well as atomic number by the precise mass measurement, and perform the decay spectroscopy by identifying by the Emaltov mass spectrograph. So using the KISS 1.5 systems, we can increase the beam intensity as one order of magnitude, and efficiency could be increased by one order of magnitude. And we can measure the many nuclei simultaneously, so the opportunity of the measurement is increased by 10 times. So the totally we will gain. We will have the gain of the 100 to the 1,000. So using these systems, we expect to access neutron-rich actinide regions up to the red lines. The blue line and purple line indicates the boundary of the known nuclides and the mass known nuclides so far. So we could access to more than 80 neutron-rich nuclei for the mass measurements, and also we can perform the lifetime measurements and decay spectroscopies by the up to the orange and the yellow lines. Okay, so if we can measure such a neutron-rich actinide region, what is the impact in the R process nucleosynthesis? This figure shows the mass deviation from the FRD models for the actinium isotopes. So far, the mass is measured up to the n equal 147. So in these regions, the different theoretical models indicated by the different lines is almost same, give the almost same values. However, beyond such experimental data, the theoretical models give such deviations. It is mainly due to the uncertainty of the asymmetric energies of the for the such high neutron ratio compared to the protons. So we could measure the actinium masses up to the n equal 157. So in this case, we could reduce the mass uncertainty around the process path regions. So this figure shows the abundance pattern from our process nucleosynthesis simulations using different theoretical mass models. And such a deviation of the asymmetric energies directly gives the yields, difference of the yields around the uranium and thorium regions. So we could reduce the uncertainty of our abundance as the actinide regions by the measuring of the masses. Okay, I'd like to summarize my talk. We are performing a spectroscopy of neutron-rich nuclei around n equal 126 and neutron-rich actinide from astrophysical interest. Especially, we are interested on the evolution of single particle energies and nuclear shapes. So we constructed keys and performing the where the nuclear production is performed by the multi-neutron transfer reaction, and the collection was made by the argon gas cell, and element selection and mass selection is possible using laser resonance ionization and ISO. And we are using the beta counter and gamma counter for lifetime and beta gamma spectroscopy and laser spectroscopy and MR for the mass spectroscopy. So we are now proceeding the upgrade of KISS 1.5 for 100 times higher efficiencies than KISS, and we find the 80 new isotopes in the actinide region. Thank you very much.
Thank you for this nice overview of the activities on these heavy isotopes. I'm just wondering about exactly your first line, nuclear production via multi-neutron transfer reactions. Mm-hmm. I was wondering if the process itself could be interesting to get information from maybe short-range correlations. I mean, multi-neutron short-range correlation, because I believe this transfer is made at once for the other nucleus. If there are some maybe idea on getting also information on that could be interesting.
Yes, it is a very interesting reaction. However, in the case of collision of heavy nuclei, this reaction ranges from the quasi-elastic region to the deeply inelastic region. So the mechanism is not direct reaction. It is very complicated, and the reaction product has excited energy. So we can only the particles after the evaporation. So it is difficult to precisely measure the mechanics of such a reaction. The Italian groups enthusiastically study such a reaction using a light nuclei, and they could find that they had evidence of that. For example, the two neutron correlation is important for such a transfer reaction. However, it is a case of the not so high excitation energies like direct reactions. But to produce the very neutron-rich side, we need more complicated exchange of the particles. So it is not so easy. We are using the gradient calculation, which is a model assuming the classical trajectories and using the form factor for the exchange of the particles. However, this model cannot explain the experimental data.
So you just transfer a bunch of neutrons at once together. This you mean?
Yeah.
In the model you use to interpret the production or whatever.
Yeah. But we'd like to transfer 6 or 8 neutrons. It is not so well understood.
So maybe I have a couple of questions. Is there any other? So going back to it was almost the last slide where you're comparing your results with the solar abundance. I mean, is the solar abundance taking care of, taking into consideration the contribution coming from the mergers, or it's just interstellar medium? The abundance, the solar abundance compared with your data, with your results, yeah, which is nice. But still, okay. I mean, you're happy with this result. I was wondering if the solar abundance accounts also for the production of our process in mergers, or it's just a core collapse supernovae.
Yes, solar abundance is indicated by the black dot, but the theory cannot explain the abundance of the actinide regions. And this is further debated using the different mass models.
Okay. Yeah, I'm not sure if this is all. Anyway, if you go back to the mass spectroscopy, your mass, the spectrum where you were showing the result from mass spectroscopy, can you tell something about the uncertainty of these single measurements? So what is the largest source of uncertainty?
It depends on the measurement. So we need the reference ions, which mass is well known for the precise determination of the unknown masses. So it depends on the situation. If there is a well-known masses near the unknown isotopes, the uncertainty becomes smaller and smaller. However, it depends on the situation.
Okay, thank you. Is coming. I cannot. Ancora no.
I just want to understand when you show the grazing calculation for multi-neutron transfer, where is there the cross section? Where is the
This one?
is the neutron transfer cross section integrated, right?
Neutron transfer, not proton is proton transfer reaction.
No, but I mean when you use different mass numbers.
This one or actinide region? Sorry. This is actinide region.
Yeah, but it's integrated over the energy range for the transfer. So how did you get that? Just the total transfer cross-sections?
This one?
I am thinking just if I could do some kind of calculation better than grazing calculation.
Yeah.
That's what I think. But for that, I need to know which kind of data you have in order to compare with.
Yeah, there are.
So if you say me, I have the transfer cross-section for between these and the energy states, then I can put something there to account for that in my mind, what I'm thinking. And then you have another point, means another proton transfer. So you don't know, you can have different two protons, one protons, or many protons transfer at the same time. But I want to know, if I do the calculations, what I have to compare with. The cross-section of what? The ground state transfer, transfer to the continuum, transfer to excited states of the residual nucleus.
Yeah, gradient calculation is not so, it is a little bit naive model. So it uses nuclear level densities in the calculation than just
level density. So probably you have a lot of levels, sure. It's
and
very heavy nuclei, so you have plenty of levels.
Yeah.
Okay, thank you.
I have one last question. Of course, it's a complete curiosity. In 24, in the slide 24, you have shown how the two-neutron separation energy moves as you increase the neutron number. I was wondering, I mean, you are still far from the drip line, no? As I see by the separation energy. But there is some guess on if we start to put that bunch of neutrons in these heavy nuclei, you can form a skin, a halo. There is some guesses on what will happen. Because I believe you would like to go along this line, no? Experimentally, no? Putting more and more neutrons on that, on the nucleus.
Yeah, it depends on the astrophysical model, but of course the process path is near the trip line, so we'd like to know the nuclear properties of the trip line. But it is very, very difficult. It is almost impossible by experiment in the present techniques. So, but there is a vast region of the unknown regions between the present known nucleus to the other process path. So, it is necessary to investigate the nuclear properties one by one for the unknown nuclear regions, especially for the actinide regions. The ratio of the neutron and the protons is very high compared to other nuclear regions. So it gives a unique opportunity to investigate, for example, the asymmetric energies, and it is important for the estimate of the around the nuclear properties around trip line.
So thank you.
So, if there are no further questions, let's thank all the speakers of this morning, and I invite the organizers to come here for the final remarks.